In this video, we're going to continue looking at another test that can be applied to a series with positive terms to determine if that series converges or diverges, right? So we're making our way through these tests, and the test in this video is called the root test. Now, if you watch the video on the ratio test, you're going to see a lot of similarities with this one, right? So there's a theorem. Fortunately, no proof. Just want to make sure that we can focus on understanding what the theorem says and how we apply it. So yeah, let's go ahead and state our theorem, and this is our theorem for the root test. And it says let our summation, so this is our infinite series, be a series with positive terms. So that means all our a sub k's are positive, so with positive terms. We are going to define R to be this. It's another limit, right? Yes, we are living in the world of limits. So R is the limit as k goes to infinity. Now, in the ratio test, remember there was a fairly straightforward ratio that we had to set up. Well, you may have guessed that because this one is called a root test, there's going to be a root that has to be set up, and here is the root. So it's the kth root of these terms, right? So just the a sub k. And let me write that in another way. So this is the limit as k goes to infinity. And remember, every root can be written as a fractional power. So if it helps you to think about the setup in this form, then go right ahead, right? So you're going to take whatever the general term of the series is, raise it to the 1 over k power, and then take a limit, and then that will give us this quantity r. And then here is the conclusion. So if r is less than 1, then the series converges. Yeah, so if our r comes out to be less than 1, then the series converges. Right. Again, it'd be nice if you had the theorem for the ratio test handy to just see how similar this is. Now, what happens if your r is bigger than 1? Then the series diverges. Right? Then the only other possibility is what happens if your r is equal to 1. So if r is equal to 1, then it turns out the series may or may not converge, right? In other words, it may converge or it may diverge. We just don't know. This is not enough information to make a definitive conclusion, right? So the series, I'll state it like this, may converge or diverge. So basically, we gain no additional information by getting an r that's equal to 1. And again, whenever this happens, what do? We try some other test. All right? So that's the theorem for the root test. Let's look at a few examples. All right? So yeah, we'll just do these. And again, I'm not going to write up the specific instructions for each of these. What we're going to do, we're going to look at a particular series and then apply this root test and see what the result is. So for example A, here is the series, and this one, just for fun, let's start it at k equals 2 going to infinity. This starting value really has no bearing on the convergence of the series, right? What has a bearing is the terms here. So let's say we have k minus 4 over 3k, actually let's make this k plus 4 over 3k plus 1 all to the kth power. And when we look at this, if you kind of think of all the tests that we've done up to this point, trying to set up any of those tests, well, some of them won't even apply. For instance, this is not geometric, right? So that won't apply. But trying to set this up as a ratio, trying to integrate, the function that is comparable to this, that won't look pretty. But this exponent that has a k tells me that, okay, if I take the kth root, things are going to simplify quite a bit, right? So again, just for emphasis, here is the terms of our series. It's k plus 4 over 3k plus 1 to the kth power. And just a quick check, k starting from 2 to infinity, right? There is nothing inside the parentheses that will produce something negative. And then you're raising that to a positive integer power. So yeah, all these terms are positive, all right? Let's write down what the kth root looks like. So that would be the kth root of everything that I just wrote down there. So we have k plus 4 over 3k plus 1 all to the kth power. And what happens with when you have a kth power inside a kth root, they cancel out, right? So you can remember that fact. But let me write down that alternative way. Let's say we express the root as a fractional power and then use just a couple, or maybe just one property of exponents. Well, I guess when you write a root as a fractional power, that's one property of exponent, essentially. So you have 1 over k. And then the other property of exponent that we're going to use is here we get to multiply the powers, right? So we're going to multiply these things, multiply these powers, and think about what's going to happen if you multiply k and 1 over k. So you'll have k times 1 over k, so that's k over k, and that's equal to 1, right? So yeah, being able to take that kth root, it simplifies our summand quite a bit. All right, and once we have it, so let's actually go ahead and write down what it simplified to. It's simply k plus 4 over 3k plus 1, right? So that's the root of the kth term. And what the test is saying now, if we can determine what happens to this expression as k goes to infinity, that's going to be our r. So r is the limit as k goes to infinity of k plus 4 over 3k plus 1. And again, notice this is an infinity over infinity case, so I'm going to go ahead and use L'Hopital's. I'm going to apply L'Hopital's here. Take the derivative of the top, that's 1. Take the derivative of the bottom, that's 3. The limit of a constant is that same constant, and that's our r. And right away we can see that this is less than 1. So the root test tells me that since our r is less than 1, then this series has to converge. So since r is less than 1, this series converges. What does it converge to? I honestly do not know what this series converges to. It's some number, right? It's some number. We just don't know what that number is. And again, just to get a sense of what's going on here, if we go back to this and let's say we just start plugging numbers in. So we start with the initial k. So we will have 6 over 7 squared. And then the next term, when we plug 3 in, you'll have 7 over 10. But now that will be cubed. And if we plug, let's say, the k after that, so if we plug 4 in, you'll have 8 over 13. But that's to the 4th power. So what our result is saying, right? And yeah, you might not be interested in a series like this, but maybe someone else is, and they might say, hey, if I continue adding up all these numbers, Will my sum just keep getting bigger and bigger and bigger, or will it actually converge to a certain number? Well, what we just did down here tells us that yes, it will converge to a certain number. We just don't know what that number is. All right. So that's our first example. Let's take another. Let's take a look at another example. Let's call that one part B. And here is my. Let's see. Now let's say k goes from 1 to infinity, and let's say we have 1 plus 1 over 3 to the k to the 6 k squared, right? All right, so there is our series, right? And the thing is, if you let's say you looked at this and say, okay, yeah, these I need to, if I were to, let's say, try to do the divergence test by just taking the limit of these terms, what you'd end up getting is basically a 1 to the infinity form, right? So let's apply our root test and see what happens. So we're going to take all of this and we're going to raise it to the, well, we're going to take the kth root, which is the same as raising it to the 1 over k power. So let me write down all of this. It looks like that. And then we have 6k squared. So let's see if we can simplify this. So there's not much that we can do with what's in the parentheses, and we'll get to that in a second. But what we can do, if we can, when we raise what's under the root to the 1 over k power, we get to multiply the exponents. So what happens there? Well, if I take k, take the reciprocal, so that's 1 over k, and multiply 6k squared, I'm going to be left with 6k. So I can cancel out the root, but I don't get rid of the entire exponent. What I get rid of is one of the factors of k. So I still have a 6 left. I still have a k left. All right? So now we have to take the limit as k goes to infinity of this, and this is how r is defined. So it's the limit as k goes to infinity of 1 plus. Now what I'm going to do, because I'm looking at this, and this does look like that special formula that we can use with our e, right? It does look like it's related to that. But in order to use that formula, I need to make sure that I only have a k in the denominator here. So I'm going to write 1 over the quantity 3k. It's the same as 1/3 divided by k. Just think about how you adjust or manipulate this fraction. You can see that these two are going to be the same, and then the 6k stays. So using our formula here, it's going to be e to the 1/3 times 6. So 1/3 times 6, well 1/3 times 6 is 2, so it's e squared. And e squared is definitely bigger than 1, right? So since r is greater than 1, then our root test says that the series diverges. Right, so this r, just because it's bigger than 1, that's all we need to know, and then that allows us to say that the series diverges. So if I go back now and just say, okay, well, what does this really mean? So I'm not going to simplify this too much, but starting with k equals 1, if you have 1 plus 1/3 to the 6th power, and then plus 1 plus 1/6, so when k is equal to 2, you have a 6 there, and 24 times 6, I'm sorry, no, 4 times 6 is 24, so then that would be my power there. And then the next term, 1 plus, when k is equal to 3, you'll have a 9 in the denominator, but then 9 times 6 is 54. So if you were to continue that pattern indefinitely, what this result down here tells us is that this summation becomes infinite. Right? All the terms are positive, And the only way, and if you keep adding more and more of those positive terms, the fact that it diverges tells us that yes, we can make our summation as big as we like, right? And that's a root test. So it all comes down to our ability to evaluate the limits, right? As we've seen, many of these tests come down to our ability to evaluate limits. And again, limits are one of the fundamental operations in calculus. So we're getting lots more practice with it, and with many hours of practice, we get close to being perfect. So perfection is kind of our limit. We will never get there, but we can get arbitrarily close with lots and lots of practice. So keep that in mind. And as usual, I'll see you in the next video.